Um, okay, so there are two more things we need to talk about with waves. I guess first, anybody have any questions? Hey, good job. Yeah. Um, any questions on like practice problems or anything? Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. Those should never, that shouldn't happen the way you're describing it. So, okay, the X and the Y, that doesn't make any difference. You could call it P or X or Y. I think I just probably called it Y because it was something that was moving up and down, and I usually call that the Y axis, you know? But whether you call it, like the name of the function is just how you refer to that function. So if you called, you could call something x of t is equal to a cosine omega t. You could call it y of t. You could call it position of t. And those are just a choice of names. Like, it doesn't matter what you call those. That's just how you would refer to it later if you talked about it, later or something. So yeah, it doesn't matter. I think probably what happened was I was calling it x of t when it was moving horizontally, and then I was calling it y of t when it was moving up and down. But you could keep calling it x of t or keep calling it p of t or whatever. Does that make sense? And the other one, if I did do that, then that's just a mistake in the solutions. So I better, what number is that? Two? And does it look like there's a mistake in there? Okay, okay. Okay. That's in harmonic motion. Okay, I'll look at that. Any other questions? When is the test? Does anyone have the syllabus in front of? I can look. It's coming up, I know. The first one? That would be a long time still. Let's just make sure while. Yeah, okay. So the night class on the 12th, the day class on the 13th. So I guess that's 2 weeks from Thursday. For the night class, it's 2 weeks from Wednesday. So that's 2/12 and 2/13. Okay, so in a couple of classes, I'll go into detail about what sets of practice problems are going to be on it. It won't be anything that we cover in the week before it, so you should have time to sort of absorb all that material. But it's definitely going to have harmonic motion and waves on it. Any other questions about stuff coming up? Problem sets, practice problems? Yeah. And all the equations that I put in boxes will be on the exam. With the exception of, I think I might have, so you should know how to do this. You should know how to derive the equation for the nth frequency of a standing wave from three equations. One is the wavelength. One is the wave speed for a transverse wave along a cable. And then the third one is the allowable waves for a string, so that's equal to 2L over N. And I mean, you don't have to be able to derive this formula in terms of the variables, but given enough to calculate, you know, these three equations, or given values that go into these three equations, you should be able to come up with the nth frequency of a standing wave. Okay, there's a practice problem like that. So I might have boxed this equation as I was going through it, but this is I'm not going to give you this one. You should be able to come up with this one from these three equations. Okay. Any questions about what I'm talking about there? Okay. So there are two more topics we have to talk about with waves. And the first of those has to do with switching. So far, everything that we've talked about with waves has been for 1D waves. So we've only talked about 1D waves. Although most of the things we've talked about apply to 2D and 3D waves also. The one thing that is different in 2D and 3D waves is, and you'll see this if you go back and look at those 5 quantities that I talked about, the one thing that's different is the amplitude. So the thing that changes in 2D and 3D waves is the amplitude. So even without any energy loss, and that energy loss would come about due to friction. The amplitude of a 2D also, although 3D is really what we're going to talk about here. The amplitude of a 2D or 3D wave at a point is different from the amplitude of the oscillator. And the way it works is, think of a sound as like a little bundle of energy, okay? So if this is the original sound source, after some small time, that original bundle of energy is now not concentrated at a point. It's spread out over, in 2D, it would be spread out over a circle because it's traveled this far in every direction in 2D. In 3D, it would be spread out over a sphere, okay? And so since it's being spread out more thinly as it gets farther and farther from the source, there's less energy in any little point in space. Does that make sense? You're just spreading that bundle of energy more thinly as it gets farther away. So this is even later. And as the time goes by, the original amount of energy is spread over a greater and greater surface area. And that's why, so you might think when you're, think about an outdoor concert or something, again, when you're far away and you don't hear the sound as loudly, you might think that that's due to energy loss, friction, things like that. And some of it is, but in fact, even if there was no energy loss, as you get farther away, you'd hear less sound. And that's because your ears are getting a smaller and smaller chunk of that original amount of energy coming from the speakers. Okay? We'll discuss intensity rather than amplitude. But it's similar. The SI units for intensity are watts per meter squared. And so that's saying, so the watts is a measure of energy per unit time. And the meters squared is a measure of area. So basically this is saying, this is a measure of how much energy you're getting at a single unit of area. Say your ear takes up, the part of your ear that lets you hear noises, that's some little unit of area. This is a measure of how much energy your ear is getting. Okay. And there's an equation relating intensity to the distance from a sound source and that says that I1, and I'll tell you what all these stand for, I1 over I2 is equal to R2 squared over R1 squared. So intensity 1 is point, like the location 1, well, that's the intensity. I2 is the 0.2 intensity. R2 is the 0.2 distance from the sound source. And R1 is the 0.1 distance from the source. Okay, so there's sort of two important things about this equation. One is that you have squares on one side and not on the other side. Okay, so this isn't a linear relationship between the intensity and the distance from the source. Okay. Where does that squared come from? Just loosely speaking, that squared comes from calculating the surface area of the sphere. You know, that sphere that I talked about that you can imagine as the sound moves out at the speed of sound, at any instant, that sound has reached some sphere because it's gone in every direction at the speed of sound. Okay, so 1 second later, it's gone far enough away in every direction to make a big sphere around the source. 2 seconds later, it's a bigger sphere. Okay. To calculate the surface area of any of those spheres, you have to take a radius squared of that sphere. That's just from the calculation of surface area, and so that's where that comes in. So that's a geometrical thing. Okay, so one important thing is the square. Remember the square, that's important. The other thing to keep in mind is notice that the subscripts flip here. So like on the left side of this equation, you're talking about 0.1 over 0.2. On the right side, you're talking about 0.2 over 0.1. And what that says is, I mean, you could figure this out for yourself, which way it goes, because you know that the intensity, which is a measure of loudness, and actually, I should have said that up here. Why don't you make a note here that's like our measure of loudness. Okay, so what you expect is that the closer you are to the source, the louder it is. Okay, so the smaller your R is, the bigger the intensity is, and that's why there's this inverse relationship. You have 0.1 on top here and on the bottom here. If you did it the other way, it would get louder as you were farther away, and then when you whispered to someone, you know, tried to talk to someone, they wouldn't hear anything you said, but you'd hear this deafening noise of people in China talking to each other and like planets doing stuff, and that would really not be a good way to live. You know what I'm talking about? Anyone still listening? Okay, so two things: the squareds and the fact that the Numerator and denominator are flipped on the two sides. All right, so let's do a little example calculation. What's the ratio of intensities for locations R1 and R2 if R2 is twice R1, okay? So in other words, how much louder is a sound at half the distance from the source? So what we have is a location 1 that's a distance R1 from the source and has an intensity I1. And we have a location 2 that's 2 times as far away and has an intensity I2. The equation that I just gave you says I1 over I2 is equal to R2 squared over R1 squared. And we can substitute 2R1 in for R2. So we get 2R1 squared over R1 squared. Now, since this is all in parentheses, to square this, you get the 2 squared and the R1 squared. So you get 4R1 squared over R1 squared. Now those cancel, and you get 4. Okay? So twice as far away, or I should say half as far away means 4 times as loud. Okay? If we were a quarter the distance away, so you had a factor of 4 difference for the distances, what would you expect the difference in intensity to be? 16. So it's always that square. Okay. Any questions about that? Well, there's one more thing that we have to consider, and that is that in talking about loudness, we don't tend to use that measure of intensity. We don't tend to use watts per meter squared. So usually, we talk about intensities in decibels. Actually, I think that's an E. So that's lowercase d, uppercase B, instead of watts per meter squared. And the reason that we do that is that there's a huge range in the intensities, if you're measuring in watts per meter squared, of what the human range of hearing is. Like a much bigger range than we're used to dealing with other units of measurement. So That's because human hearing ranges from about 10 to the minus 12th watts per meter squared to around 1 is when it can start to do damage to your ears, in watts per meter squared. And that's just a huge range. It's cumbersome to use a mathematical range that big. So we use decibels instead, which range for us something closer to, well, low numbers, 5, 1, whatever decibel, up to 100 or 150 or something. It's a more manageable range of numbers to deal with. But so we're going to use decibels to talk about intensities, but we have to do our calculation in watts per meter squared, then we need two things. We need a conversion to go from decibels to watts per meter squared, and we need a conversion to go from watts per meter squared to decibels. Okay. So we need two conversions. And that is beta is equal to 10 times the log base 10 of I over 10 to the minus 12, where beta is the intensity in decibels, and I is the intensity in watts per meter squared. So this is the conversion you would use if you knew the intensity in watts per meter squared and you wanted to express it in decibels. And the other conversion says the intensity in watts per meter squared is equal to 10 to the power of beta over 10 minus 12. And those are just inverse functions of each other. You could, that's the kind of calculation that I'm sure you did in college algebra. But here it's done for you. And if anybody today or later when you start to work on these problems needs help figuring out how to do this in your calculator, come talk to me. We can figure it out. Because these aren't buttons that you have to use very often, like log base 10 and 10 to non-integer powers. So feel free to come talk to me about that. All right, let's do an example. So let's say that 50 meters from a speaker, John Boehner, say, you measure, that was like a play on words. You measure 58 decibels, okay? That's loud for a person. So how many decibels would be perceived at a distance of 200 meters? So notice that we can't use this I1 over I2 is equal to R2 squared over R1 squared with decibels. So we're going to have to take the 58 decibels, convert that to watts per meter squared, do this calculation, and then convert our answer back into decibels. Okay, and that's a pretty common thing you're going to have to do in these problems. So 58 decibels is going to have to go to watts per meter squared. Then you're going to have to use this equation. And then watts per meter squared is going to have to go back into decibels. So to convert 58 decibels into watts per meter squared, you have I is equal to 10 to the power of 58 over 10 minus 12. And so that is, 58 divided by 10 is 5.8. Subtract 12 and you get I have 6.3 written here. That's weird. It's 6.2 though. So 10 to the power of negative 6.2. Yep.
So on in the x to the 10, like it's 50 over 10, is that 10 to the negative 12 or is that minus 12?
That's minus 12, but it's still in the exponent.
Okay.
So if you remember like exponent rules, another way you could think of that is you have 10 to the 5.8 times 10 to the minus 12. Okay, and if you plug, does anyone know how to do this with fractional powers? Because my answer must be wrong. I wrote the wrong thing here. Anyone? Can I use this for a second? Okay, so on these TI calculators, there's a 10 to the X button, and so now you just go second 10 to the X, plug in your answer, and you get 6.31 times 10 to the minus 7. So 6.31 times 10 to the minus 7, and that's in watts per meter squared. And now we can plug that into this relationship between intensity and distance. So 6.31 times 10 to the minus 7. So now I guess let me just point out what I'm doing here. So I'm calling this 50 meters when it's at 58 decibels. I'm calling that my location 1. And this I'm calling location 2. So the intensity at location 1 is this. The intensity at location 2 is what we're trying to find. The distance at location 2 is 200. The distance at location 1 is 50. And what you get here is what we talked about last time. These distances are different by a factor of 4, so your intensities are going to be different by a factor of 16. And so that's what you get. This value is going to be 1/16 of this value. So I2 is equal to, you're just doing that algebra and you get 3.94 times 10 to the minus 8 watts per meter squared. And then the last thing we have to do is just express that back in decibels. So the intensity in decibels is 10 times the base 10 logarithm of 3.94 times 10 to the minus 8 divided by 10 to the minus 12. And you get 46.0 decibels. And so you can see from the answer why it wouldn't work to do the intensity distance relationship in decibels. In watts per meter squared, we had a factor of 16 difference between the two, but in decibels, the difference was only from 58 to 46. That's not a factor of 16. It's not even a factor of 2. So you have to first go to watts per meter squared and then convert. Any questions about that? Okay, one more thing we have to talk about is the Doppler effect. Okay, so I have an example of the Doppler effect here. Let's see. Okay, so the start of this song, great song, there's like a car horn going and you hear it at one pitch and then like the car goes by the observer and it changes to another pitch. And that's what the Doppler effect is. You get a change in frequency depending on how quickly something's moving towards you or away from you. I don't think that's really a car horn, actually. I think that's a synthesizer, but. Is that really how it sounds? Is this the real version? Okay, so that's the Doppler effect. You get a change in frequency depending on whether something's moving towards you or away from you. Okay, we should probably listen to this song for a while. Okay, that's enough. Okay, so you hear it with car horns, like when that's never an enjoyable time, but so somebody goes by you honking their horn at you, you hear the car horn, it sounds like it's at one frequency as it's coming towards you and then a different frequency as it's going away from you. Okay, that's the Doppler effect. The frequency perceived is different if the sound source is moving towards or away from the observer. Or if the observer is moving toward or away from the sound source. In either case, moving closer together creates a higher perceived frequency and moving farther apart creates a lower perceived frequency. And here is how you calculate that. So I'll tell you what all these variables mean, but f prime is equal to f times a big fraction. The top, the numerator, is the speed of sound plus or minus the speed of the observer. And the denominator is the speed of sound minus plus the speed of the source. This f prime is the perceived frequency. This regular f is the produced frequency. And for the plus minus and minus plus. The top operation in each case means moving toward, one moving toward the other. So, in other words, both moving toward each other means f prime is equal to f times the speed of sound. If they're both moving toward, we take the top one here, the plus. So plus the speed of the observer. And on the bottom, we have the speed of sound. The top operation on the bottom is the negative. So speed of sound minus the speed of the source. And it also makes sense, if you don't remember just that little rule, you can also remind yourself that if they're moving towards each other, the perceived frequency is getting higher. So think about what it takes to make this fraction bigger. The numerator has to get bigger and or the denominator has to get smaller. Okay.